Okay guys, so this is a, a review lesson for sinusoidal functions for our unit exam. So I've got a handful of questions that I've taken from the standards and exemplars for this course. And what I want to do here is just show you the question. You could pause the video, attempt it, and then afterwards I'll go through an explanation of how to find the answer. So I would pause it here and give this a try, and then when you're ready, I'll go through the explanation. Okay, so hopefully you came up with an answer to this. The height of a pendulum, h. So over here, our y value is the height in inches above a tabletop t seconds after the pendulum after the pendulum is released can be modeled by the sinusoidal function shown below. So here our variable t is for time in seconds. And I'll just change the thickness of that pen. There we go. So the height, the question is numerical response, the height of the pendulum at the moment of release. So the moment of release means time 0. And we have to round to the nearest tenth of an inch. So for this question, we have two ways that we could solve it. The first being graphically in the calculator. And I would simply I would simply enter this equation as my y1, and then I would just do second trace value for x equals 0. And then I could determine the answer that way. The other way is to do it algebraically, and I would say, what is the height when time is 0? So 2 sine 3.14 times 0 plus 1.57, and then add 5. So if I put this into my calculator, the answer that I get is 6.999. So that's 7, but to the nearest tenth, I have to put in 7.0. So the correct answer to this one is 7.0. So next, a multiple choice one. This one, the height above ground of a rider on a Ferris wheel can be modeled by the sinusoidal function given here, where h is the height of the rider above ground and t is time, this case in minutes, and height is in meters. So slightly different, but give this one a try. Maybe pause the video here, and then I'll go through the explanation after. Okay, so here we're looking for the maximum height. And in any sinusoidal function, if I just draw one here, so let's say we have this function. We know that this is the midline, this is d, y equals d, right? Our midline of the function. And we also know that this distance here is a, the amplitude. So the maximum, which would be this point at the top of that peak, the maximum is the midline plus the amplitude. So if I look in my equation, we should all know that 6 is the value for A, and 8 is the value for D, and 6 plus 8 is 14. So my maximum occurs at 14. Hopefully you picked answer D. Okay, here's another one. Looks like the same Ferris wheel. Okay, I just copied and pasted this part again, the sort of preamble. This time you have a numerical response when the rider is at least 11.5 meters above the ground, she can see the rodeo grounds. During each rotation of the Ferris wheel, the length of time that the rider can see the rodeo grounds to the nearest tenth, so again, watch your rounding, of a minute is blank minutes. So give this one a try. All right, so what you might do in this question is put the equation into your calculator. So I would make this y1, and then 11.5 would be my y2. And so in my calculator, I should see this function. So looking, whatever, something like this. Okay, maybe it looks slightly different. And then 11.5 being this line here. So this is 11.5, and the curve here is our function h, this guy. Okay, I put that in. And basically what we're interested in is how long can she see the rodeo grounds. So I want to find these two x values and see how much time is this. So when I sketch this in the calculator, the rider starts seeing it at approximately 2.09 minutes, and then finishes seeing it at 3.89 minutes. So if I subtract those, then the amount of time that she can see the rodeo ground should be 1.8 minutes. So this one's a little bit trickier in that we have to find both of these values, and then this segment up here is when she's high enough up in the Ferris wheel to see the rodeo grounds. Okay, next one, the average daily high temperature of Montreal in degrees Fahrenheit for each month of the year is shown in the table below. January is month number 1, that makes sense. February is 2, and so on, going up to December over here. So when we see a table like this, we're probably doing a regression. And if we look down here, the question is to write a sinusoidal regression function of the form a times sine bx plus c plus d, outside of the brackets there, where x is the month number and y is the average daily high temperature that could be used to model these data. Round them to the nearest hundredth. So here's a good practice with regressions. Give that a try right now. Okay, so hopefully you all were able to find the regression for this equation, and also I hope you rounded it correctly. And the equation that you should come up with is y equals 29.08 sine of 0.51 x minus 2.02 plus 50.77. So there's a good regression question for you, just a bit of practice. All right, let's see what else we got. Okay, I think this is the last question, and the graph of a sinusoidal function is shown below. There it is. And numerical response says possible values for the amplitude and median of the sinusoidal function are 10, 20, 30, 40, and 50. Record the values of the amplitude and the median of the sinusoidal function above in the blanks. So you need to put a 2-digit number here, and your choices are these guys. So give that a shot. Okay, so if I'm looking for the median and the amplitude, I can see that my lowest point is at 10, and my highest point is at 50. So if I add those up and divide by 2, that's going to give me my median, which is at 30. And I would bet a lot of you didn't bother doing that calculation. You can just see it on the graph that that's the median. And so that's fair too. So let's fill that in. The median is 30. And if I go back to my picture, the amplitude I can see from the midline to the max. This is the midline again. That's my maximum. I can see that that's 20. The other way I can do it is from the midline to the minimum, and that's also 20. So the fact that that's the same distance there and there confirms that I've placed the midline in the correct spot. If they were different, then that wouldn't be the right midline. So this should be 20 and 30. Oh, and we have one more, my bad, one more. So the graph of a sinusoidal function is shown below. The points A, B, C, D, and E are labeled, as you can see. Points A, C, and E lie on the midline, so there they are. And that dotted gray line here is the midline. Mary says that in order to find the period of the function, she would need to know the coordinates of the points A and E. Bill says that he could find the period using the coordinates of B and D. Both Mary and Bill are correct. Explain why. So what I'd like you to do when it says explain is write in words. So take a minute and write down an explanation as to why they are both correct. Okay, so what you should come up with here is an explanation as to why Mary is correct and why Bill is correct. So for Mary, I would say that the horizontal distance between A and D A and E, excuse me. She said A and E. Would be the period. So if I look back here, that is from right when we numbered this 1 to 3 back to the midline, 4 to the minimum, and 5 back to the midline. This horizontal distance is the period. So that is the wavelength, is the period, the length of time to complete one cycle. Whereas Bill says the distance between B and D. So B is the maximum and D is the minimum, and he's taking only this distance from here to here. And so I would say Bill is also correct because that distance is half the period. Bill is also correct. He's using half the period. So he would simply double it. So he should double that distance. And that's true when we measure the distance between a maximum and a minimum. This is half the distance. And you can even kind of see here, right? We've separated it into like 1, 2, 3, 4 segments, and Bill has 2 of those 4. So that idea of measuring between the max and the min horizontally should work as well. All right, that's it.